Welcome to Industrial PLC Application. This is the third part in a series called First Steps. This video is on understanding the first instructions used. Let's review the instructions we used in our first initial program. To clarify, let's define what we mean by instruction. An instruction is a logic device placed in a ladder logic program that instructs the PLC how to interpret the status or state of a location in memory, or perform a task or alter a location in memory. Instructions collectively form a ladder logic program. Let's begin by looking at the most common instruction, XIC, execute if charged. This instruction is the original contact instruction, and the way I have it shown is how it would have appeared on a printout or on the CRT display. In a relay logic, it would be known as a normally open or open circuit contact. However, to a PLC, it's not about the state of a set of contacts. It's about the status of a single bit or bool of memory, or in the case of a switch, whether the switch is passing current onto the PLC's input terminal. If we follow the current from the 24-volt power supply, we can see how the XIC instruction will work. With power supplied, the PLC will examine the current state of each input. Inputs DI00 through to DI02 have no voltage at the terminal because they are normally open switches. But DI03 is a normally closed switch, which allows current to reach the input terminal screw. In Connected Components Workbench, you would find that even though the circuit is incomplete, the input DI03 is highlighted as active or energized. In the real world, a digital multimeter would confirm there is voltage on DI03's terminal screw. In Connected Components Workbench, the mnemonic XIC has been updated. The tip wizard in the software reveals it is now called a direct contact. On all future exercises, we will be referring to this instruction as a direct contact. XIO, execute if off. This instruction is the second most used instruction in PLC programming and is essential to verify if something is not working or to confirm an action has taken place. As the name suggests, this contact is the opposite of the direct contact, and in fact it is now called a reverse contact. It also makes NOT logic possible. Without delving too deep into NOT logic is looking at negative inputs to allow something to happen, and we will cover this in detail in a later video. XIO, execute if off. The opposite of XIC is XIO. This instruction tells the CPU to examine the logical value of a memory location and only continue executing the logic if the location is off. With the above example, the energized state of input DI03 is active. An XIO instruction of that input terminal tells the CPU to examine the logical value of a memory location and only continue executing the logic if the location is off. Rung 3 has 3 XIO instructions in series. They are 3 unpressed, normally open push buttons. Because the instruction tells the CPU to continue executing the rung if these are not energized, the rung is true and the output DO01 is energized. Since the instructions are highlighted, it may seem confusing. If an XIC is highlighted, then the CPU is acknowledging the memory location is energized and therefore true. If the XIO is highlighted, then the CPU is acknowledging the memory location is de-energized and therefore true. Allow me to clarify the last statement. In relay logic, we deal only with tangible hardware, things that we can test using a meter or activate by pressing a button. With PLCs, you can perform more tasks with less wiring and hardware because inevitably, all real-world inputs and outputs are converted or reduced into internal memory locations. But this also means you can create as many internal relays as you desire. Well, until you run out of PLC memory. In the above example, rung 3 is made up entirely of internal relays and bits. This is one of the greatest advantages of the PLC. Internal relays can perform logic just as effectively as real-world ones, only faster and more reliably, since there are no moving parts or wires that can be broken or miswired. Furthermore, they allow you to test out logic, and if the logic works as expected, you simply replace the internal relay's contacts with the addressing or variable names with the real ones. OTE, output energize. This is the first actionable instruction. This instruction turns outputs or internal variables on. It is now called a direct coil, and it is the workhorse of all output-oriented instructions. When energized, the PLC changes the state of a memory location from off to on. Now that we are on the subject of turning something on, it's important to associate a key operation that is taking place within the PLC. PLCs basically have three broad categories of instruction-related actions: read, write, or manipulate, or take special actions, which are generally reading, calculating, and writing, or some variation. Read instructions are instructions that the PLC performs to evaluate the condition of a memory location. Read instructions are non-destructive in that they do not alter the state or value of a variable, but simply look at it. Write instructions are instructions that the PLC performs that will take action to change or maintain the value or condition of a memory location. Write instructions are considered destructive instructions since they always overwrite any existing states or values. Non-changes are actually the same state rewritten. Returning to our direct coil. Direct coils can be either a real-world output or an internal variable, but not both. This has to do with the naming convention used to prevent PLC and human confusion. Direct coils only work on a single bit or bool of memory and has only two conditions: on, which will be shown as a 1, or off, which will be shown as a 0. Direct coil instructions are write or destructive instructions, as they will always overwrite a variable's value. The two rungs above demonstrate the operation of the direct coil. In the first rung, there is no clear executable path because the PLC has read the three inputs and determined that DI_03 is not charged and therefore does not get executed. This results in the direct coil output DO_07 to be de-energized. In the second rung, both internal_bit.0 are energized and internal_bit.1 is energized, which satisfies the logic, and the PLC energizes the internal direct coil internal_bits.31. The above two rungs have a problem. Neither has an output. Rung 1 is an empty rung and it's dead short. Rung 2 asks the PLC to evaluate input DI04 and execute the logic if it is true. If this were a relay logic scenario, it would be a dead short waiting to happen. In Connected Components Workbench, these do not create a problem because the software and the Micro 850 know you weren't paying attention and basically ignores these errors. However, most other PLCs and software may not tolerate this situation. If the software does not catch these errors, then the PLC itself will have a major fault and shut down. Make sure you do not leave unexecutable rungs in your program. This is not an unexecutable rung because it has a valid output instruction with a valid variable. It's called an unconditional rung because the output has no conditions before it. It's not a mistake, but rather a rung that will continually energize the output. As programmers, we need to control everything in our program, and this rung has no way to turn it off. This rung has very limited applications, mostly for showing the PLC power is on and is executing the logic. The top rung shown has an unusual instruction. It is not an input or read instruction, nor an output or write instruction. It's not even a manipulating instruction. In fact, it does nothing. And that's the point. NOPs or NOPs or no operation instructions can be used to create a blank canvas rung to record vital, user-friendly information about the program so the next electrician can quickly ascertain what the intention of the program is. The top rung is called a header rung. NOP instructions are also used as placeholders. So if a currently unknown or undecided input instruction is to be added later, a spot for it in the program can be held as shown in the bottom rung. Notice on the bottom rung it appears to be having no influence on the rung, but that is only because the first contact is currently energized and the PLC is looking for it to be off in order to continue executing the logic. But look what happened to the top rung. In the top rung, the programmer created an accidental operational rung with unwanted execution flow. The NOP in the branch does nothing, but the branch containing the NOP acts to short out the variable IO_I_03, and the other NOP shorts out the rest of the logic. NOPs are intended to do nothing, not to circumvent the logic, so when using them, be mindful of where they are placed. In this three-part series, we covered creating a project, creating a ladder logic program, creating rungs of logic, and 4 new instructions: XIC, XIO, OTE, and NOP, otherwise known as direct contact, reverse contact, direct coil, and NOP. This series of videos should have acted as a review of your first day of the PLC lab. The lab covered a lot of essential ground, and this video should fill in some of the blanks and provide deeper understanding of the instructions you used in your first 9 rungs of logic. The next series of videos will explain the behavior of the PLC and how it solves logic. Thanks for watching.